Good evening, children.
Good evening, ma'am.
Good evening. Good evening, children. Okay. So continuing from where we stopped yesterday, this was the question where we stopped yesterday. The second exercise of circles. We finished in the 11th one, continuing with the 12th one. A triangle ABC. Children, I've shared my screen. Is it visible?
Yes, ma'am.
Okay, thank you. Yeah. A triangle ABC, as you can see in the figure, is drawn to circumscribe a circle. The triangle circumscribes the circle. Triangle is outside. Triangle circumscribes a circle. So circle is inside, the triangle is outside. Of radius 4 centimeters. The radius of the circle is 4 centimeters, such that the segments BD and DC, the segments BD, this is BD, this is BD, and this is DC. This one is DC. This is BD, this is DC. Okay, such that the segments BD and DC into which BC is divided. Yeah, this is BC. Let me just darken that. Okay, so BC is a side of the triangle ABC, and BC is divided into two segments, not bisected. Bisected is different, divided is different. So it's divided into two segments, DC and BD. BC is divided into two segments as it's given in the question. BD is one segment and DC is the other segment. Okay, so CD is given to be 6 centimeters and BD is given to be 8 centimeters. So you can see the segments BD and DC into which BC is divided by the point of contact D. Yeah, D is the point of contact. BC, the side BC of triangle ABC acts as a tangent to the circle. The side BC of triangle ABC acts as a tangent to the circle at D. The point of contact is D. Okay, so find the sides AB and AC. You need to find the length of the sides AB and AC. We know that BC is 14 centimeters. BC is 8 plus 6, 14 centimeters. You need to find the lengths of the sides AB and AC. Okay, so triangle circumscribes a circle with center O. The three, which means the three sides of the triangle are tangential to the circle. The three sides of the triangle are tangential. They act as tangents to the circle. Now, the side BC is a tangent to the circle at D. So BC is divided into two parts, DC and DB. DC is 6 and BD is 8. Given this, we need to find the lengths of the remaining two sides of the triangle. Very simple, the procedure to find the answer. Step 1 is to join the center of the circle to the vertices of the triangle. That is, you have to divide the whole triangle ABC into three smaller triangles. We have to divide the whole triangle ABC into three smaller triangles. So let's join OA, OB, and OC. Okay, this is A, B, C. Let's join OA, OB, and OC. So when you join OA, OB, and OC, you see that you've divided the whole triangle into three smaller triangles. Okay, now we have to find the further proceeding, or we have to find the areas of the three smaller triangles. So for that, you need the base and altitude. Now, when you take this triangle BOC, the base is BC. Altitude will be this one. OD is the altitude. We know by the theorem that the radius and the tangent at the point of contact are perpendicular to each other. Radius and the tangent at the point of contact are perpendicular to each other. right? So D is a point of contact and DO is the radius through the point of contact. D is a point of contact, DO is a radius through the point of contact. So this is 90 degrees. So for triangle BOC, which is the base, BC is the base, and which is the altitude, OD is the altitude. Like this, for the other two triangles, you need to identify the base and the corresponding altitude. So for triangle AOC, if you take AC as the base, you know that AC is a tangent to the circle. So let's say this is the point of contact. This is the point of contact. Join the point of contact to the center. Join the point of contact to the center. So you know that this is 90 degrees by the theorem. And that is the corresponding altitude. So if you call this E, OE is perpendicular to AC. Why is OE? What is OE first? E is the point of contact and we join E to O. That is E to the center of the circle. So EO is the radius. And that's a radius through the point of contact. So it's 90 degrees here. Radius tangent perpendicular to each other. Same thing here. Let's mark this point of contact as F because AB is a tangent. Let's say at F, join F to O. So radius and radius tangent perpendicular. 90 degrees. So for this triangle AOC, if you take AC as the base, then OE is the altitude. And for the other triangle AOB, this triangle AOB, if you take AB as the base, OF is the altitude. So this is the equation. Okay, you can see it here. I'll show the figure on the next slide later. Okay. So what's the idea? The idea is to divide the whole triangle into three smaller triangles by joining the center O to the vertices A, B, and C. Now we have three smaller triangles. We need the altitudes of the respective triangles. For that, we join the point of contact to the center. That will be the altitudes of the three triangles. Because by the theorem, these angles will be 90 degrees. Now the equation is area of triangle AOC plus area of triangle BO. This is O, the center of the circle. Here is O. Area of triangle AOC plus area of triangle BOC plus area of triangle AOB is equal to area of the whole triangle ABC. This is the equation. This is the equation. So working with this equation, you will get the answer. That's all it is. This is the equation. Area of the sum of the areas of the three small triangles is equal to the area of the whole triangle ABC. Now, how many points we see in this figure? We see about 6-7 points in this figure. Point O lies inside the circle. It's the center of the circle. The points D, E, and F, they lie on the circle. The points D, E, and F, they lie on the circle. So which are the points outside the circle? A, B, and C. A, B, and C are the points outside the circle. And we have tangents to the circle from these outside points A, B, and C. So you can see that AF and AE are the tangent segments from the external point A to the circle. AF and AE are the tangent segments from the external point A to the circle, and they're equal. Similarly, B is an external point to the circle. B lies outside the circle, right? So BE and BD are tangent segments from the tangents or tangent segments from the external point B to the circle. So BE is equal to BD by the theorem. The tangents from an external point to the circle are equal in length. So BE is equal to BD. Similarly, C. C is an external point. So CD is equal to CF. Now, CD is actually 6. So CF is also 6. BD is 8. So BE is also 8 by the theorem. Let's call AF as X. So AE is also X. And what about OD? Radius R. OE, radius R. OF, radius R. So OD, OE, OF, R, radius R. What about, they are the altitudes. Okay, and what's the length of BD? 14. 6 plus 8, 14. What's the length of AC? X plus 6. And what's the length of AB? X plus 8. So like this, we know the bases and the respective altitudes. Now for the whole triangle ABC, we cannot use the formula half base into height for the whole triangle ABC because we don't know the altitude to any side. So we have to use Heron's formula. To find the area of the whole triangle ABC, we'll have to use Heron's formula. For the three small triangles, you can use the formula half base into height because for a base, you know the corresponding altitude. But for the whole triangle ABC, you have to use Heron's formula. That's all it is. Let me show you the next slide. So see here, children. Area of triangle AOB. AOB. Where is AOB? This one. This one is AOB. This is AOB. Okay, base x plus 8 into radius. Radius is given here. 4. This is R, right? This is R, 4. So 4. See here, half into base x plus 8. Area of triangle AOB. AOB is half into base x plus 8 into altitude 4. So on working that, you get 2x plus 16. Area of triangle BOC. BOC is half into 14 into 4. And area of triangle AOC is equal to half into x plus 6 into 4. So we found the areas of the three small triangles. Now the area of the whole triangle ABC. Area of the whole triangle ABC. Okay, you can see here I've added area of, I found the sum of the areas of the three small triangles. It's 4x plus 56, 4 common, x plus 14. See here. Area of triangle AOB plus area of triangle BOC plus area of triangle AOC. This plus this plus this. You get 4x plus 60, 4x plus 56, 4 common, x plus 14. So that's the sum of the areas of the three small triangles. Now, calculation of area of the whole triangle ABC using Heron's formula. So you have to find the semi-perimeter, which is the sum of the three sides by 2. So you know the sides, no? We just substituted. X plus 8 is one side, x plus 6 is one side, and 14 is another side, right? X plus 8, x plus 6, and 14. So A plus B plus C by 2. So you get 2x plus 28 by 2. 2 common here. 2 is common. So you'll get x plus 14 in the bracket. 2 and 2 cancel. So x plus 14. So semi-perimeter is x plus 14. Now what's the formula to find area? Square root of s into s minus a into s minus b into s minus c. So square root of s, x plus 14 into s minus a, x plus 14 minus a. This is a. Into x plus 14, s minus b, this is b, s minus c, this is c. So you'll have to be very careful because you'll have to write s minus a in a bracket because a has more than one term. S minus a, this is s, this is s, minus a, you should not write minus a like this. This is s minus a in bracket because a has more than one term. So this is s minus a everywhere in bracket. See, s minus b we did not put in a bracket. This is s minus b because b is just 14. So you don't need a bracket there. So be careful. And then you can say x plus 14, x plus 14, minus x minus 8, x plus 14, minus 14, x plus 14, minus x minus 6, minus x minus 6. So x plus 14 as it is. Here x and minus x cancels. So 14 minus 8 is 6. Here plus 14 minus 14 gets cancelled, x. And here x minus x cancels, 14 minus 6, 8. So 6 8s are 48. 48x, you can see here 48x, 48x, and this x plus 14, x plus 14. So the area of triangle ABC is square root of 48x, 6 8s are 48x into x plus 14 centimeter square. Now we know that this one is equal to this one. The sum of the areas of the three small triangles is equal to the area of the whole triangle. So this is the sum of the areas of the three small triangles. 1 is equal to the area of the whole triangle. 2. 1 is equal to 2. So I call this 1, call this 2. So 1 is equal to 2. So write that. And to get rid of the square root symbol, you'll have to square on both the sides. To get rid of the square root symbol, you'll have to square on both the sides. So squaring on both the sides. See, how do you do that? See, like this. Squaring on both the sides. Squaring on both the sides like this. If you write 4 into x plus 14, the whole square like this, wrong. You should square the LHS and RHS completely. So whatever is in the LHS, enclose that in a square bracket, square. Whatever is in the RHS, enclose that in a square bracket, square. So that's what you see here. That's what you see here. So now this will become 4 square 16 and x plus 14 the whole square. X plus 14 the whole square. The square should be applied for everything inside the bracket. So we have 4 and x plus 14. So 4 squared 16 and x plus 14 the whole square. X plus 14 the whole square. And here the square and the square root will get cancelled. So you will have, that is the square root is eliminated. When you square here, the square root is eliminated. So you will have 48x into x plus 14. 48x into x plus 14. Now, you cannot actually x plus 14 is common on both the sides, but you should not divide by an expression which contains the variable because you will lose, like if you're going to get two values for the variable, you lose one of the values. If you want to, get both the values of the variables, if there are two values, if you want to get both the values, you should not divide here by x plus 14. You see that x plus 14 is common on both the sides, right? You should not divide both the sides by x plus 14. You can divide by a constant, but you should not divide by an expression that has a variable in it. If you do that, you will get the answer. Like what's the answer here? Okay, minus 14, 7. X is equal to minus 14 or x is equal to 7. You will only get x is equal to 7. You will not get this value x is equal to minus 14. So you might think, okay, anyways, minus 14 we are not going to take. So what if we don't get it? You will get this value. I'm just telling you the difference. If you divide by x plus 14, what will happen? You will not get x is equal to minus 14 as a solution. You will not get this. This one is a solution, but just that it does not fit into this condition because here we're dealing with line segments. So x cannot be minus 14. Otherwise, it is a solution. So that's a difference. So I have not divided by x plus 14 on both the sides. Like I haven't done this, dividing by x plus 14 on both the sides. No, because I want to see both the values of x. Okay, so I divide by 16 on both the sides. So dividing by 16 on both the sides, you can see 16 cancels and then you can see a 16 ones are 16 threes are. So we have x plus 14, the whole square is equal to 3x into x plus 14. After simplifying, 3x, x plus 14. Now have all the expressions on the same side. So I've transposed. All right. Next, I take out x plus 14 common. X plus 14 common. Now, this is like, this is like say a squared minus 3xa. A squared minus 3xa. So what will you do? A is common. Then in bracket, a minus 3x. a minus 3x. So here, between this expression and this expression, x plus 14 is common. So bring out x plus 14. And then in the bracket, x plus 14 the whole square. So you should write 1 x plus 14 here, because x plus 14 into x plus 14 is x plus 14 the whole square. And this one, x plus 14 is common here. So you should write this minus 3x inside the bracket. Minus 3x. See, it's like, I'll just remove this whole square and write x plus 14 here. So this x plus 14, this x plus 14 is common here, right? Write the remaining inside the bracket. So write x plus 14 minus 3x. The remaining things you should write it in the bracket. This one is, sorry. This one is common outside. So x plus 14 minus 3x in the bracket. So this gives you 14 minus, this gives you 14 minus 2x. So x plus 14 into 14 minus 2x is equal to 0. And then you know x plus 14 is equal to 0, x is equal to minus 14, which is not possible. Okay, because what is x here? X is the length of a line segment. You can see here, this is x. And this cannot be negative, right? So x is equal to 14, not possible. So on solving this one, 14 minus 2x is equal to 0, we get x is equal to 7. The question is to find AB and AC. Okay, AB and AC. So what is AB? How much is AB? AB is x plus 8. AB is x plus 8. And x is what? 7. So AB is 7 plus 8, 15. And AC is equal to 7 plus 6, 30. So the sides of the triangle are 15 and 30. Okay, so what we had to do? We had to divide the whole triangle into 3 smaller triangles. So we had to connect the center of the circle to each of the vertices like this. This is the first step, dividing the whole triangle into 3 smaller triangles. Then point of contact, point of contact, point of contact. The 3 sides are tangents, points of contact. Join the center to the point of contact, center to the point of contact, center to the point of contact. So radius perpendicular to tangent, radius perpendicular to tangent, radius perpendicular to tangent. So for the 3 small triangles, we have their altitudes. So you can find the area of each of the small triangles using the formula half base into height. Add half the answer. Then find the area of the whole triangle ABC using Heron's formula. Equate these two. To get rid of the square root symbol, square on both the sides. Do not divide by x plus 14 because it has the variable x in it. Instead, bring all the expressions to one side. Take out x plus 14 common. So you get one negative value for x, one positive value, negative not possible. So go ahead with the positive values and then find AB and AC. And also, this is 6, this is 8. So if this is 6, this is 6. If this is 8, this is 8. So we assume this one is x. So this is also x. Because tangents from external point to the circle are equal in length. So this side becomes x plus 6. This side is x plus 8. And this one is 14. This one radius is given 4. Radius is given 4. Given 4. Prove that the opposite sides of a quadrilateral circumscribing a circle. So quadrilateral circumscribes a circle. Quadrilateral is circumscribing. So quadrilateral is outside. The circle is inside. Prove that the opposite sides of a quadrilateral circumscribing a circle subtend supplementary angles at the center of the circle. Okay. Let me just try to draw. Okay, just ignore this extra. Yeah. So here we have a quadrilateral circumscribing a circle. Okay. Now, which are the let me call the quadrilateral ABCD. ABCD is a quadrilateral. Now, the opposite sides are AB and CD. AB and CD are opposite sides. Now, the angle subtended by the side AB at the center is angle AOB. Angle AOB is the angle subtended by side AB at the center. Angle COD. This is the angle subtended by side CD at the center. Like you should join C to O and D to O. Join C to O, D to O. This angle is the angle subtended by side CD at the center. Join A to O and B to O. This angle is the angle subtended by AB, side AB at the center. So these are the two angles subtended by the opposite sides, AB and CD at the center. You must prove that these angles are supplementary. You must prove that this angle plus this angle is equal to 180 degrees. Similarly, the other pair of opposite sides are AD and BC. AD and BC. AD subtends AOD at the center. AD, side AD subtends angle AOD at the center. Side BC subtends angle BOC at the center. Angle BOC at the center. You need to prove that these two angles add up to 180 degrees. We'll have to prove that the opposite sides of a quadrilateral circumscribing a circle, they make supplementary angles at the center. Opposite sides make supplementary angles. So we understood the angles are subtended by the opposite sides. You must prove that the angles are supplementary. That is, this angle plus this angle is equal to 180, and this angle plus this angle is equal to 180. There are four angles formed, no? Angle AOB is made by side AB. Angle COD is made by the side CD, opposite sides. So you must prove that the sum is 180. Similarly, BOC is made by BC and AOD is made by AD, opposite sides. You must prove that the sum is 180. So now this is done using congruency. Just a second, children. Yeah. So see here. Yeah, children, I'm back. So look at the figure here. Now, the other thing we have to do is to join the points of contact to the center. You can see the points of contact are P. P is a point of contact. AB. AB is a tangent. P is the point of contact. Join P to O. BC tangent. Q point of contact. Join Q to O. Similarly, join R to O and S to O. This one we already joined to understand the angles AOB, BOC, COD, DOA. This one we already connected to understand the opposite angles, the angles made by the opposite sides. Apart from this, what you have to join is join the points of contact to the center. Okay. So you'll have to draw a circle. You'll have to draw a quadrilateral outside the circle, touching the circle outside the circle. And then you should mark the center of the circle as O, join OA, OB, OC, OD, and also join the points of contact to the center. Now, as I told you in the last class, which are the external points? A, B, C, and D. These are the external points. The other points are on the circle. P, Q, R, S, they are on the circle, and O is inside the circle. O is inside the circle. P, Q, R, S, they are on the circle. The points outside the circle are A, B, C, and D. Now, BO is B is an external point. BO is a line segment joining the external point to the center. Take the two triangles on either sides of the line joining the external point in the center. Which two triangles we have to consider and show are congruent? Look at all the lines from the external point to the center. There are 4 lines from the external points to the center. There will be 2 triangles on either sides of these lines. You'll have to show that those triangles are congruent to each other. So let's see the lines from the beginning. A is an external point. A is an external point. AO. AO is the line segment from the external point A to the center. On either sides of AO, we have this triangle and this triangle. Show that these 2 triangles are congruent. Next external point is B. External point is B. BO is the line segment joining the external point to the center. These are the 2 triangles on either sides of BO. Show that they are congruent. Next, C. CO is the line segment joining the external point to the center. And these are the 2 triangles on either sides of CO. Show that they are congruent. And this one and this one. DO on either sides of DO. And how do you show that they are congruent? As we saw in the last class, we have more than sufficient information. So you can use RHS, SSS. We have a lot of information here. So you can use SSS. How does that work? In this triangle and in this triangle, we'll just do this for example. Everything else can be proved in the same way. So in these 2 triangles, you can see that BO is the common side. Then OP is equal to OQ, radii of the circle, and BP is equal to BQ. Tangents from the same external point to the circle are equal, or tangents from an external point to the circle are equal. BP is equal to BQ, all right? Then OP is equal to OQ, radii, and this is the common side. BO is the common side. SSS rule. Or you can use RHS also. You can use ASA. Okay. Many. RHS, you can say right angle. Here also right angle because radius perpendicular to tangent. Hypotenuse, common side. Meaning hypotenuse, which is the common hypotenuse. And some other side. Right angle, hypotenuse, and any other side. You can say this side is equal to this side. RHS. Okay. So use any of these congruence rules to show that the triangles are congruent. So when you show that this triangle is congruent to this triangle, angle 2 is equal to angle 3. When you show that this triangle is congruent to this triangle, angle 1 is equal to angle 8, CPCT. This triangle is congruent to this triangle, angle 6 is equal to angle 7, CPCT. And this triangle congruent to this triangle, CPCT, angle 5 is equal to angle 4. Okay. Now, see here, once you write all these results by CPCT, I'll just show you here. See, these 2 triangles are congruent, result by CPCT. These 2 triangles congruent, result by CPCT. So like that. Now we know that the sum of all the angles around a point is 360. So add all these angles equated to 360. Now what do you want to prove? What do we want to prove? We need to first show that AOB, which is angle 1 plus 2, 1 plus 2, AOB plus COD, 5 plus 6. We want 1 plus 2 and 5 plus 6. So you want 1 plus 2, 5 plus 6. You don't want the others. Because 1 plus 2 is angle AOB and 5 plus 6 is angle COD. So you don't want 3, 4, 7, 8. So let's replace 3 with what? What is 3 equal to? 2. You can see it. 3 is equal to 2. So instead of 3, you say 2 in the next step. And you don't want 4. So instead of 4, 4 is equal to 5. So we'll replace 5. And we don't want, have I ticked it correctly? Yeah. We don't want 7. Instead of 7, what? 6. See here, 6. And we don't want 8. And instead of 8, 1 angle 1. That's what is done in the next step. In the next step. That's what you see here. You can see that there are only angles 1, 2, 5, and 6. 2 times. Twice we have. Because we have replaced. You should identify the angles you want. You want to prove angle AOB, which is angle 1 plus 2, plus angle COD, which is 5 plus 6, is equal to 180, supplementary. So you don't want 3, 4, 7, 8. So replace with their equals. When you do that, you get this. So you see twice of angle 1 plus twice of angle 2 plus twice of angle 5 plus twice of angle 6 is 360. Take out 2 common. And then the 2 goes for division here. So it becomes 180. Now what is 1 plus 2? Angle AOB. What is 5 plus 6? COD. So you proved that AOB plus COD. You proved that the opposite sides subtend supplementary angles at the center. Now you know that the sum of the 4 angles around the point is 360. We know that the sum of the 4 angles, angle AOB, we know that AOB plus BOC plus COD plus DOA. We know that the sum of these 4 angles is equal to 360. The sum of the 4 angles around the point is 360 degrees. We know that. Now we proved that AOB plus COD is 180. AOB plus COD is 180. So when you substitute that, you will get BOC plus AOD is equal to 180. 360 minus 180, which is 180. BOC, this one, plus AOD is also 180. Correct? No, if this plus this you have proved is 180. If you have proved this angle plus this angle is 180, what's the remaining? 360 minus 180, 180 is remaining. So that should be the sum of these 2 angles, right? That's what we have shown here. The statement will be given, children. The figure will not be given. You need to understand the statement and draw the figure for yourself. Prove that the opposite sides of a quadrilateral circumscribing a circle subtend supplementary angles at the center. With that, we come to the end of NCRT. Now over to extra problems. Okay. So first find X. So we know that this is 90 degrees because radius tangent perpendicular to each other. Radius tangent perpendicular to each other. So 90 plus 90, 180 gone. We also learned yesterday, we proved there was one question in the second exercise where we had to prove that this angle plus this angle is equal to 180. This is the angle between the 2 tangents. Remember, this is the angle between the 2 tangents. This is the angle between the line segments joining the points of contact to the center. I don't remember the question number, the second exercise somewhere in the end. This is called the angle between the tangents. The tangents are PA and PB. This is the angle between the tangents. What is this angle called? This angle is the angle between the line segments, joining the points of contact to the center. A and B are the points of contact. A is a point of contact, B is a point of contact. AO and BO are line segments joining the points of contact to the center. So in that particular question, we had to prove that the angle between the two tangents and the angle between the line segments joining the points of contact to the center, these two angles are supplementary. We had to prove this. That was simple because this angle is 90, this is 90. So 90 plus 90, 180. So 360, this is a quadrilateral. PAOB is a quadrilateral. PAOB is a quadrilateral. So 360 minus 180. 180. So the sum of these two angles have to be 180 degrees. You can use the same property here. So the special name, a special name to this quadrilateral OAPB is it's a cyclic quadrilateral. It will always be a cyclic quadrilateral. What is a quadrilateral? A quadrilateral in which one pair of opposite angles are supplementary. A quadrilateral in which one pair of, when one pair is supplementary, the other pair, when one pair of opposite angles are supplementary, the other pair of opposite angles are automatically supplementary. But this is the definition. A quadrilateral in which one pair of opposite angles are supplementary is a cyclic quadrilateral. So OAPB is a cyclic quadrilateral. This plus this is 180. So this plus this is also 180. So clearly x is equal to 158 degrees. X is 150. Because 150 and 30 make 180. That's about x. And then we have to find BOP. BOP. So we'll have to join. Okay. So show that these two triangles are congruent. So CPCT, you will have this angle equal to this angle. These two triangles are congruent. You know, you can use SSS, RHS, whatever. Show that these two triangles are congruent. So this angle is equal to this angle. So BOP is this one. The whole angle is 150. So this one will be 75 degrees. The whole of x is 150, right? And what is BOP? It is half of x, because once you show that the triangles are congruent, this angle is equal to this angle. So 150 by 2, 75. BPO, where is it? Okay, BPO, here, this angle. BPO, this angle. That'll be 15, because the whole angle is 30 degrees. And again, now the triangles are congruent to each other. So CPCT, this portion is equal to this portion. This angle is equal to this angle. The whole angle is 30 degrees. So 30 by 2, 15. Or you can use angle sum property also. You can use the angle sum property. You can say that you just found that this is 75, right? So 75 and this is what? 90. This is 90. So 90 plus 75. Then 180 minus that answer will give you this. But you can do CPCT. Just show that these two triangles are congruent. This angle is equal to this angle. This angle is equal to this angle. That's it. So this is by using the property. So in the, I think that was 10.2, no, circles, 10.2, I think. Okay, so in that second exercise of circles, we have learned this property. When a quadrilateral circumscribes a circle, the sum of the opposite sides are equal. We proved that. When a quadrilateral circumscribes a circle, the sum of the opposite sides are equal. Which are the opposite sides? AB and CD are opposite sides. Sum of the opposite sides. Then AD and BC, opposite sides, sum of the opposite sides, they're equal. Equal. This is a property we learned. So 4 plus 8 is equal to AD, we don't know, plus 7. So work this. So it will be 12 minus 7 is equal to AD. So AD is equal to 5. AD is equal to 5. You don't have to prove that result. You don't have to prove that result. You can use that result straight away. You don't have to prove it. You can mention that. We know that when a quadrilateral circumscribes a circle, the sum of the opposite sides are equal. And then you can write this result, substitute and find AD. So this property also we, I think, just learned. Yeah. The last question, second exercise, last question. Prove that when a quadrilateral circumscribes a circle, the opposite sides subtend supplementary angles at the center. When a quadrilateral circumscribes a circle, prove that the opposite sides subtend or make supplementary angles at the center. So we know that x plus 85 is equal to 180. They're not vertically opposite angles, please, because we don't have straight lines here. AOOC is a broken line. It's not a straight line. BOOD is a broken line. It's not a straight line. Okay, so don't say vertically opposite. Don't say vertically opposite angles are equal. They're not vertically opposite. You should use the property x plus 85 is equal to 180. X plus 85 is equal to 180. So x is equal to 95. You should mention that property. See, when a quadrilateral circumscribes a circle, its opposite sides subtend supplementary angles at the center. Write that and then same thing here. X plus 80 is equal to 180. Y plus 95 is equal to 180. X plus, because you can see circle, outside you can see a quadrilateral. Inside circle, outside quadrilateral. So x plus 80 is equal to 180. Opposite angle supplementary. Then 95 plus y is equal to 180. Okay. So in this figure, if the sides of the quadrilateral ABCD, if the sides of the quadrilateral ABCD with some measurements are given, if the sides are tangential to the circle, so you can see that the sides of the quadrilateral act as tangents to the circle. With center O, find the value of R. So you need to find R, children. R. Very simple, but most common question from circles. Very simple to understand. Listen to this. We need to first prove that this quadrilateral is a square. Remember, in this figure, we'll have to prove that this quadrilateral, this one, is a square. Now, how do you prove it's a square? First, prove it's a rectangle. And in a rectangle, when adjacent sides, when one pair of adjacent sides are equal, it's a square. Last year, quadrilaterals, 9th standard quadrilaterals. Prove it's a rectangle. And in the rectangle, if one pair of adjacent sides are equal, it's a square. Okay, so we'll prove it's a rectangle first. So in this figure, children, this angle is 90 degrees is marked. It's given to us. Okay, this we haven't found. This is given. Now we know this is 90, radius tangent perpendicular. We know this is 90, radius tangent perpendicular. So now by the angle sum property of a quadrilateral, this is also 90 degrees. Because 270 360 minus 270, 90. Now in this quadrilateral, you can see opposite angles are equal. That's how you should say. Because every corner, okay, every corner is 90 degrees, so it is a rectangle, that's also fine. Or you can say opposite angles are equal. You remember 9 stand? No, actually, I'll tell you, you can even say all angles are equal to 90 degrees, so it's a rectangle, that's fine. But I'm coming from the definition. Opposite angles are equal, so it's a parallelogram. And in the parallelogram, one angle is 90 degrees, so it's a rectangle. If you can recall from 9th standard, the definition of a rectangle. A parallelogram in which one angle is a right angle is a rectangle. Okay, now I think we'll not do that. We'll just say that every angle is a right angle, so it's a rectangle. That's enough. Okay. It's a rectangle. Now in this rectangle, one pair of adjacent sides are equal. See here, OP is equal to OQ. Because radius, no? Radius of the same circle. OP is equal to OQ. So in the rectangle, one pair of adjacent sides are equal. You can even show that this is equal to this. How? Because they're tangents from an external point of the circle. B is the external point. BP is equal to BQ. One pair of adjacent sides are equal in the rectangle. So it's a square. So OPBQ is a square. Now that it's a square, all the sides are equal. Now that's a square, all the sides are equal. So if this is the radius, this cannot be the radius, but the value is equal to the radius. BQ is not radius. The length of BQ is equal to the radius, is equal to the value of the radius. BP also is equal to R. Now, we'll start with, see here, AB is 29. Let me just mark it, children. AB, where is AB? This is 29, children. This is 29, okay? AD 23. AD, this full thing. This one is 23. DS is 5. DS, this is 5. Let me just bring this figure to the middle. 1 second. Yeah. Yeah, so this is R, this is R. Yeah, we're given that DS is 5, children. Where is, yeah, see, DS, this is 5. This one is 23. 23. And this one is 29. 29. Okay. All right. Now, DS is equal to DR. Okay. DS is equal to DR. So, DR is 5. So, AR will be 23 minus 5 because the full thing is 23. So, AR will be 23 minus 5, 18. If AR is 18, AQ is 18. If AQ is 18, then BQ will be 29 minus 18, 11. That means R is 11. And hence the radius of the circle or the value of R is 11. So you'll all agree it's very simple. You just have to prove that this one is a square. This is a square. So all the sides equal to R. Now this is given to be 5. So this is 5. But the full thing AD is 23. So this will be 23 minus 5, 18. Now if this is 18, this is 18. This one is 18. But the full thing AB is 29. So QB will be 29 minus 18, which is 11. So R is equal to 11. And DS is equal to DR because tangents from the external point D to the circle are equal. Similarly, AR is equal to AQ because tangents from the same external point A. Find the perimeter. So this is 4, this is 4, this is 6, this is 6, 5, 5, 3, 3. Now find the perimeter. You know all the sides, find the perimeter. This side is 11, this side is 8, this one is 7, this one is 10. So add all the 4 sides to get the perimeter. AS 6. B 7, 6 plus 4, 10. 6 plus 5, 11. The question is to find the perimeter of the quadrilateral. We'll do the numericals tomorrow, children. We'll do these tomorrow. In this time, I just do simple ones now. All these numericals are take time, no? So we'll just take it up tomorrow. Just check something. Yeah. So we know that P is an external point. P is an external point. To both the circles, P is an external point. Only P is an external point. The other points lie on the circle. P is an external point. You can see that PQ will be equal to PT and PT is equal to PR. PT is equal to PQ. How much is PT? 3.8. So PQ is also 3.8. Also PT is equal to PR. So PR is also 3.8. So how much is QR then? QR is this one from here to here. This is 3.8. This one is 3.8. So 7.6. 7.6. P is an external point. So PQ is equal to PT. Tangents from an external point of the circle are equal. PT is equal to PR. So now PT is given 3.8. So PQ is 3.8. This is also 3.8. So QR is equal to 7.6. So in this figure, we are given that AB is equal to 5, BC is equal to 7, and CA is equal to 6. We need to find the radius of the circle with center A. Find the radius of the circle with center A. Okay. Now these are not tangents because we've been seeing tangents all the while. No, suddenly, no, these are not tangents. Okay, they're the radii. You can see that AP and AR. They are the radii of the circle with center A. So you can call it X. PP and BQ. They are the radii of the circle with center B. So you can call it Y. CQ and CR are the radii of the circle with center C. So Z. Now, we are given that AB is equal to 5. If AB is 5, what is AB? X plus Y. Can you see? AP is X, PB is Y. X plus Y is equal to 5. Then we have BC is equal to 7. And what is BC? BC is Y plus Z. Y plus Z is equal to 7. And then we have CA is equal to 6. And what is CA? CA is X plus Z. X plus Z is equal to 6. So like this, we have 3 equations, children. We have 3 equations. Somewhat similar to this, we have done in coordinate geometry. So I'll just show you the next slide. So after constructing equations like this, okay, I just showed you, no? Okay, after constructing the equations like this, add the three equations. See, we constructed three equations, right? Add the three equations here. Add. So you will get 2x plus 2y equal to 18. 2 common is equal to 18. So x plus y plus z is equal to 18 by 2, 9. Now x 9. What should you find actually? You should find the circle with center A. I think we called it, what is APY? It's called Y, children. Here it's called Y. Here AP and A are called it Y. That is the radius of the circle with center A. Okay, Y. So we need to find Y. So I've substituted for x plus z. We have to find Y, right? So we have this equation x plus y plus z equal to 9. We need to find Y. So substitute for x plus z. X plus z plus y is equal to 9. What is x plus z? 7. 7 plus y is equal to 9. Y is equal to 9 minus 7, 2. Another 5 minutes, children, I'll wind up. Find the value of R. Children, use the emoji, raise your hand. Tanishka, Prenu, Swati, Niveda, Blessing, Ratsa, Hari Pranav, Bhavishya, Devarshini, Srivatsam. Aniruddhan is not there. All right. Very important, very simple, very important. Find the value of R. All right. Join. This is the point of contact. Tangent. Okay, so the three sides of the right, this is a right triangle. The three sides of the right triangle are tangential to the circle. The circle is the in circle to the right triangle. We'll have to find the value of R. So here also prove that this quadrilateral is a square. Prove that this quadrilateral is a square. Same method. There also in that figure, one angle was given 90 degrees. So here also the right triangle, one angle is given 90 degrees. There also in that figure, one angle was 90 degrees. Here this is 90 because of the right triangle. This one is 90 because radius perpendicular to tangent, radius perpendicular to tangent. So the fourth angle is also 90. And this is the rectangle. In the rectangle, adjacent sides are equal. So it's a square. Now that it's a square, this one is R. Now the whole thing, actually, this is the whole thing. When this, this full thing is 7. This full thing is 7. Now, what is this? This is R. So this will be 7 minus R. The rest of it will be 7 minus R. And let me mark things. Call this B, and this one is E. All right. 19. Okay. Now, children, BC is 7. BC is 7. I'll correct the meaning I'll make it more clear, the image, when I share it with you. Okay, BC, or I'll include that in the question. BC is 7. Now this one is R. All the sides are equal. It's a square, so each side is equal to R. So DC will be 7 minus R. BE is also R. Because all sides are equal. It's a square, so R. So AE will be 24 minus R. The full thing is 24. Bottom little portion is R. So the top portion will be 24 minus R. R. This is R. So the rest of it is 7 minus R. This is R. So the rest of it is 24 minus R. Now we know that AE is equal to, let me mark this as F. We know that AE is equal to AF. Why? tangents from an external point to the circle are equal. So this one is also 24 minus r. Similarly, we know that CD is equal to CF. Tangents from the external point to the circle are equal. So this is 7 minus r. This is also 7 minus r. But by Pythagoras theorem, we know the hypotenuse is 25 centimeters. 24 and 7, 576 plus 49, 625, square root of 625, 25. So we know that AC is 25 by Pythagoras theorem. But what is AC here? It is AF plus FC is equal to 25. What is AF? 24 minus R plus what is the FC? 7 minus R is equal to 25. So this is the equation. This is the equation. AC is equal to 25 by Pythagoras theorem. But AC is AF plus FC, 25. AF is 24 minus R and FC is 7 minus R is equal to 25. So 24 plus 7, 31 minus 2R is equal to 25. So 31 minus 25 is equal to 2R. So R is equal to 6 by 2, 3. So radius of the inner circle is 3 centimeters. The value of R is 3. Yeah, this I'll just share this also with you. There is a formula, like if it's an MCQ, you don't have to spend so much time. Okay, the in radius is given by sum of the legs minus hypotenuse by 2. In radius is equal to sum of the legs of the right triangle minus the hypotenuse by 2. C is the hypotenuse. A and B are the legs. R is equal to sum of the legs minus the hypotenuse by 2. So sum of the legs 24 plus 7 minus the hypotenuse 25 by 2. So this is 31 minus 25 by 2, 6 by 2, 3. 1 mark. You don't have to, like spend so much time showing where it's a rectangle, then a square, and then all that you don't have to do. The earlier method is for more than 1 mark. It's 1 mark, you can just do it like this. Sum of the legs minus hypotenuse by 2. So this is time consuming. We'll just do it tomorrow. The idea is the same. We saw a similar question in NCRT, no? We just have to join the center to the vertices, then show the altitudes, and then area of the 3 small triangles. Sum of the areas of the 3 small triangles is equal to the area of the whole triangle. That's all. That's the equation. And you'll, like find whatever you have to find PQ. You can see that here. That's the idea. Yeah. In this one also, children, see, AD is X, AF is X, BD is Y, B is Y. This is Z, this is also Z. This whole side is 8 and this side is 14. So what are the 3 equations you'll get? X plus Y is equal to 14. Y plus Z is equal to 8. X plus Z is equal to 12. 3 equations. There we got such equations because radii, they were the radii of the same circle. But they are tangents from an external point of the circle. That's why this is X, this is also X. This is Y, Y. Z, Z. So you'll get the 3 equations, write them one below the other, add the equations and okay. Okay, I'm winding up this one, just 2 minutes. In this figure, PRQ is equal to 120 degrees. Listen carefully. PRQ is 120. This angle, PRQ is 120 degrees. You'll have to show that OR, which is OR, this is OR. 1 second, please. This angle is 120 degrees, PRQ. We need to show that OR is equal to PR plus RQ. Step 1. P to O, Q to O. Show that these two triangles are congruent. CPCT, this angle is equal to this angle. The whole angle is 120. So it will be 60 here and 60 here. Take up any one of the two triangles. Both the triangles are right triangles. Take any one of the two triangles. Say you take this one. This is 90 degrees, right? Because radius tangent perpendicular to each other. Now this is 90 degrees. Now you need to connect. Now the angle you know is 60 degrees. You can also find this angle. This will be 30 degrees by angle sum property. So you need to connect either 30 degrees or 60 degrees with, look at the result here, OR, PR, RQ. OR, where is OR? This is OR. Now I'm just showing one triangle, children. I first connected both. I told you that you'll have to show that those two triangles are congruent. And CPCT, you have the result. This angle is equal to this angle. This is 60 degrees. Okay, so now we are dealing with this triangle. And this is 60, so this will be 30. Now look at the result here. OR, PR, RQ. OR, this is OR. PR, this one is PR. And RQ is here. Okay, leave that. RQ is a part of the triangle we have taken. So leave that. Now OR and PR. So you'll have to connect 60 degrees or 30 degrees. Now we'll take 60 degrees. You'll have to connect 60 degrees with OR and PR. Connect 60 degrees with OR and PR. Now this OR is the hypotenuse because it's opposite the right angle. OR is the hypotenuse because it is opposite to the right angle. Now for 60 degrees, PR is the adjacent side. For 60 degrees, PR is the adjacent side. And OR is the hypotenuse. So cos 60 degrees. Cos 60 degrees is equal to adjacent PR by hypotenuse OR. Why are we connecting these two sides? Because we just looked at this result. We have OR and PR. OR, PR, which are sides of this triangle. RQ is not of this triangle. So leave that. So we are connecting 60 degrees with OR and PR. Because we have, so we are connecting 60 degrees with OR and PR. For 60 degrees, PR is the adjacent side and OR is the hypotenuse. So cos 60, what's the value of cos 60? 1 by 2. 1 by 2 is equal to PR by OR. So you get OR is equal to 2 times PR. OR is equal to 2 times PR. So we're close to the result. We have to show OR is equal to PR plus RQ, but we've got OR is equal to twice PR. Now OR is equal to twice PR, meaning PR plus PR. So OR is equal to PR plus, we know that PR is equal to R cube because tangents from an external point of the circle are equal. External point is R. RP and RQ are the tangents from R. So they're equal. So PR is equal to RQ. PR is equal to RQ. So we got the result. OR is equal to PR plus RQ. OR is equal to PR plus RQ. The result has OR and PR. RQ is not a part of this triangle. Earlier we joined OQ. We showed that these two triangles are congruent. The whole angle was 120, so 60-60, CPCT, so 60-60. So we take up this triangle and we connect 60 degrees with this side and this side. This side is the hypotenuse. So we have to connect 60 degrees with PR and OR. So cos 60 is equal to the adjacent side PR by the hypotenuse OR. Cos 60 is 1/2 is equal to PR by OR. Cross multiply, you get OR is equal to twice PR. Twice PR can be written as PR plus PR. OR is equal to PR plus PR is equal to RQ. Because R is external point. RP is equal to RQ. So for this RP, you can just put RQ. And that's the result. All right. All right, children. So that's it for today's session. Thank you so much. You can leave the call. Good night.
Thank you.
Thank you, children. Good night.